Hello everyone, my name is David O'Reilly and I'm going to present to you the investigation into the temperature dependence of novel inorganic scintillation detectors, which formed my final year project as part of my undergrad studies at the National University of Ireland, Galway, with the help of Kashan Qayyum, Majed Alharbi and Mark Foley. So first off, what do I mean when I say a scintillation detector? Well, as I'm sure you're aware, scintillation is the emission of light from a material when it is struck by a high ionizing radiation or a high energy particle. Now, scintillation is a well-established method for detecting ionizing radiation. Rutherford himself used a zinc sulfide screen in his gold foil experiment. So the technique is clearly well utilized and understood. Now, recently there has been interest in applying scintillation to the clinical setting in dosimetry in radiotherapy by coupling a scintillating material to the tip of an optical fiber to transmit the light. The exact design for these detectors is pictured here on the right. A 3mm deep, 700 micron diameter hole is micromachined into the core of the fiber. Scintillating powder is packed in, sealed with an epoxy, and then wrapped in insulating tape. And these optical fiber dosimeters, which is what I will refer to them as, have a number of properties which make them desirable. First of all, they are small in size. They're quite compact devices. The outer polyethylene jacket, as you can see on the right, is only 2.2 millimeters in diameter. So they could be used in keyhole type surgeries by positioning them beside a tumor to measure the dose and check if it matches up with a prescribed dose. Also, they are immune to electromagnetic fields due to the lack of metallic components inside them. Thus, they can be used in image-guided radiotherapy in conjunction with MRI. Thirdly, their rather simple design has the added benefit of being rather relatively cheap to manufacture and create. And they also have the benefit of giving real-time dosimetry. The light is transmitted along the fiber as it is being produced, and there is no need for processing after exposure to a dose like other methods. So all of these features in conjunction with one another make the realization of optical fiber dosimetry in the clinical setting a realistic one. So the 4 scintillating powders used in this study, 3 of them were gadolinium oxysulfates doped with terbium, praseodymium, and europium, and a 4th zinc sulfide scintillating powder was also used. Now, scintillating materials can be broadly categorized into 2 groups, organic and inorganic, and the differences between the two arises from their fluorescence mechanisms and their subsequent properties. Firstly, the organics. The fluorescence mechanism arises from transitions within the molecule itself. Thus, it is independent of state, and this makes them quite versatile. They can be polymerized into plastics and made into a variety of shapes and sizes. They're characterized by their short response times, which makes them ideal for ultra-fast counting. The inorganics, on the other hand, their fluorescence mechanism arises from transitions within the lattice structure itself. Thus, you have bandgap considerations to take into account. They're characterized by their longer decay times but superior light output. And on the table on the right, you can see just a summary of what I've just said. The green ones are the organics, and you can see their response times are in the order of nanoseconds, whereas the inorganics underneath are much higher, some of them on the order of milliseconds even. However, on the far right column, you can see the superior light output of the inorganic scintillators. So whether or not a scintillating material would exhibit a temperature dependence would be, as you can imagine, quite an important parameter. Depending on the temperature of the environment, you could have perhaps a redshift or a change in intensity of the signal output. So it's important to account for. Sam Badar's research group, who do a lot of work on organic scintillators, actually investigated this, and they found that temperature does have a significant impact. And on the right, you can see a plot from one of his papers. The top plot being an overlay of spectra for different temperatures, which visually shows the change in decreasing intensity with increasing temperature. And then the bottom plot shows the percentage change in signal intensity with per degree Celsius. And you can see the largest change is at the peak, similar to the plot above. However, the temperature dependence in inorganic scintillators is yet to be gauged. So motivated by this work, this is what we set out to do. Primarily because these devices are to be used in a clinical setting for in vivo dosimetry, which is at 37 degrees Celsius. That's 15 degrees above room temperature. So if this has an effect on their signal output, it should be accounted for. So here's a schematic of the experimental setup. A water bath consisting of a hot plate and a beaker of water was used to subject the optical fiber dosimeters to a range of temperatures. A feedback thermometer provided feedback to the hot plate so it could adjust and achieve a steady temperature. An additional thermometer was also used, which was accurate to 0.1 degrees Celsius, rather than using the one on the hot plate, which is only accurate to 1 degree. An additional bare fiber, pictured there in orange, was used, was also irradiated. This is because when optical fibers are irradiated, they can produce Cherenkov radiation inside of them. This, coupled with noise and ambient, is known as stem effect in dosimetry, and it is something we want to get rid of. The bare fiber is capable of only producing stem effect. Thus, when a subtraction technique is done, we can isolate the fluorescent signal to get cleaner data. So just a quick mention of how we collect the data. A HR4000 spectrometer was used in conjunction with OceanView software to capture and save and view spectra. As for temperature readings, 5 degree Celsius increments were chosen for a temperature range of 15 to 40 degrees. 5 spectra are captured for each fiber at each temperature stage, with an integration time on the software of 5 seconds. In the image on the right, you can see a green crosshairs, and that indicates the isocenter of the LINAC beam. So we positioned our detectors as best we could across that. A 10 by 10 centimeter field size was used to ensure good irradiation of the entire beaker, and 492 mu per minute was delivered by the LINAC. Thus, for a 5-second scan, that's approximately 41 mu, or 0.4 grays of dose, absorbed dose. So by following the mentioned procedure, we obtained the following spectra. A color-coded convention is used throughout, of blue through to red being cold to hot. One thing to note straight away is the relatively poor performance of the europium and zinc sulfide fibers. Neither of them went above even 100 counts. Thus, the signal to noise ratio of them is very poor. However, the terbium and praseodymium fibers perform quite well, especially the terbium one, which had nearly 700 counts, double that of the praseodymium one. So because of this, we limited our data analysis to the terbium and praseodymium fibers. Shown here are the normalized spectra for the terbium and praseodymium fibers. They're normalized to themselves at their lowest temperature. And the same color-coded convention was kept throughout, so the blue through to red being cold to hot. So in order to see if there's any visual change in these in the intensity, we zoomed in on the peaks and fit a smooth trend line to visualize the data. And shown here is a select wavelength range. So we zoomed in on the peak for the terbium praseodymium spectra. For the terbium one, there doesn't seem to be any clear trend other than a bit of noise. So there doesn't seem to be any clear downward trend or upward trend of intensity. However, for the praseodymium one, there does seem to be a clear downward trend of intensity with increasing temperature. So in order to put numbers on all of this, we plotted intensity versus temperature. To calculate the intensity, we simply calculated the area under the graph for each temperature stage, for each temperature spectra. So shown here are intensity versus temperature graphs for the same wavelength range for the terbium and the praseodymium fibers. The terbium graph doesn't seem to suggest any strong relationship. The R-squared value leaves a lot to be desired, and a confidence interval on this regression line also contains 0 for the slope. Thus, we could not conclude any significant relationship between intensity and intensity of light emitted by the terbium phosphor and temperature. However, for the praseodymium, there does seem to be a clear downward trend of intensity with increasing temperature. There's a good R-squared value to back this up, and as well as that, a confidence interval on the slope did not contain 0. So as well as this, we also conducted a brief test of signal repeatability. So for each point's error, we plotted that against temperature also. And shown here for the terbium and praseodymium fibers, there does seem to be a clear upward trend of signal error by approximately 0.3 or 0.3% increase in error with per degree Celsius for both fibers, interestingly. The praseodymium fiber does seem to have a stronger correlation or squared value of 0.95. However, the terbium fiber does still have a good fit. So overall, the findings were that the praseodymium phosphor had approximately a 0.24% decrease in signal intensity with per degree Celsius, and the R-squared value there is quoted. The signal repeatability also increased with temperature by approximately 0.03% per degree Celsius. The terbium phosphor, on the other hand, did not show any significant relationship between the intensity and temperature. This is shown by the confidence interval on the slope containing 0. However, interestingly, signal repeatability tests showed the same increase in error by approximately 0.03% increase per degree Celsius. However, overall, they could not conclude that terbium fiber had a significant temperature dependence. So, to conclude, the praseodymium fiber displayed a significant temperature dependence, and if to be applied in the clinical setting, a correction factor should be considered. The terbium phosphor, on the other hand, is a strong candidate for in vivo dosimetry. Its large signal intensity and light output, coupled with its weak temperature dependence, or non-significant temperature dependence, makes it a strong candidate for in vivo dosimetry. So here are some references that I used, and I'll be happy to answer any questions if anything was not clear. And I would just like to thank the IEE conference for allowing me to present my work. Thank you for listening.